All right. Hey, everybody. This is Mark B. from Bangladesh, Wayne out in northern Colorado, and Alan in Alabama. And we are here for our second week of ecological solar design. And I'm not going to spend very much more time other than just to say we are so grateful to have Alan. He was amazing last week, everybody. Any of you that did not listen, if you are an Eat Free member, you still can get his replay probably up until sometime over the weekend from last week even, and watch it. And I would highly recommend that because it was amazing. And I know tonight's going to be great, and we're going to, he's going to do at least 8 or 9 more weeks, and it could be more than that. So that said, one last thing, a couple more sessions tomorrow. We actually got a very cool 3 hours scheduled on Friday, which is kind of our meet the members, and we've got 3 different people that we're going to have some presentations for, and one fella who is pretty special. His name's Samir. He's at Ambery Gardens, and I think this is pretty accurate. I think they're the only hemp production facility in the U.S. that's using aquaponics, and he's going to talk about their experience with that. And then here's an interesting one. They're at 9,000 feet, folks. Obviously, they're indoors, and they produce year-round, and they're producing their own CBD. So they do extraction, the whole works. So they are a soup-to-nuts kind of operation, and we're pleased to have Samir with us tomorrow during that session. So I'm not going to spend more time talking about how to find it and such. If you want to put it in the question, if you don't know how, we'll answer it, and I'm going to turn it over to Alan. I'm going to mute myself. So everybody, here we go.
All right, and welcome everybody to our second session of Ecological Solar Design. And what we're going to do today is, as I was planning out the course, I realized that since we are going to be talking about solar PV and solar electric as a major part of what we're doing, not the only thing, but a major part of it, that it would really be important for me to go back and do what we're going to call Electricity 101. And for some people, this will be mostly review. I'll try to throw some things in there that are kind of interesting for you. But for a lot of people, I've realized as I've talked to them, a lot of the terminology that goes on around electrical circuits and power and so forth, they've heard them, they may be a little vague. And what I want to do is make certain that we spend a few minutes getting everybody just comfortable with the vocabulary and the concepts we're going to be using through the rest of this series. So we're going to do that tonight. And but I did want to start off first with just a little quick review of some of the key concepts from last week, and where we talked about solar photovoltaic, and it being the piece part of solar design is all about generating electricity, but that we wanted to see if we could first meet all of our other needs, as many needs as possible in our designs, through using solar more directly, using things like passive solar heat, direct solar hot water heating, cooking with the sun, and even high efficiency wood burning systems. And then look at using electricity only for high-value loads. And we're going to come back and really talk about what those high-value loads are. And by doing that, we're going to eventually start looking at it as our goal to use 90% less electricity in our ecological solar designs than is typical in, let's just say, an average house or building. And that's going to be one of the things that's going to inform our thinking as we go. And it may not be possible if you're just retrofitting a standard house, but if you're moving in that direction, you're going to be much better off. So what I want to do is just start really basic and think about what is electricity. The thing is, if you're in modern life, you're surrounded by it all the time. And we talk about it, but unless you've had physics or an engineering class or gone to school as an electrician, then maybe it's a pretty vague thing. It just is magic that runs around inside the house around you or inside the buildings around you. It makes things happen, but you really haven't had to think about what it is and how it works too much. So there are actually a lot of different forms of electricity. There is, as the previous slide was showing, there's lightning, there's static electricity that you get when you walk across the carpet and touch something that's grounded, and there's other forms of electricity, but the type that we are talking about for our purposes today, the type we use in homes, buildings, vehicles, electronic devices, and so forth, that consists of an electric current that is flowing through a circuit. And what we mean by that is electric current is just basically a bunch of electrons that are being pushed along by some electromagnetic force, and they run through what we call a circuit. And a circuit is, we're going to look at what a circuit is in a little bit more detail later, but if you can just think of a circuit as basically a bunch of wires and devices hooked together that create a complete path. And so I'm going to start with this analogy that I found to be really helpful for people who are just still starting to get their head wrapped around electricity. And that is, I want you to think about electric current going through a circuit as being something of an analogy to water flowing through plumbing. The difference is we have electrons that are flowing instead of water, and that those electrons are flowing through wires instead of pipes. So that's going to help us out a lot in sort of getting our head wrapped around how it works and some of the basic concepts of electricity. And, you know, I'm an electrical engineer, so, you know, just the things we do with electricity, if I have to think my way through it and go back through all the classes I've taken and so forth, they come down to basically two main things that we use electricity for. One is to provide power. That is to power something, whether it be a motor or an electronic device, you know, or to provide power to a heating element to heat something up, like your hot water heater if you have an electric hot water heater. There's a lot of ways we use electricity just to provide power. And the other way we use electricity is to carry information. So right now I'm sitting here talking to you on my computer. It's got an Ethernet cable coming out the back and going into the router that lets me talk to the, you know, back over the internet. And that is copper wire, and that signal is being carried with, you know, very low power, low voltage electric current going back and forth in a very particular way. And that's what's carrying the information. So in general, if you think about it, those are the two main ways that we are going to use, we end up using electricity in modern life. And yeah, you know, the telephone line that brings the telephone in here is same thing. It's information being carried on electricity over wires, and there's a lot of places that you see that. Your USB port on your phone, all of those are electric power carrying information. But as we start looking at solar PV, and we're going to be talking about producing electricity to provide power. So just wanted to kind of have us think about that and think about what we're really doing here is we need to produce the kind of electricity that is of the type and scale required to power our loads. So I want to start with some really basic terms to make certain we're all on the same page as we go forward. And the first two things to talk about in working with electricity is a conductor and an insulator. So a conductor is simply a material that allows electricity to flow easily, where an insulator is a material that resists or blocks the flow of electricity. So the pictures I have here, one is copper wire, and copper wire is what we use most of the time for carrying power. Excuse me. And then in the lower left, that is a glass insulator that used to be used a long time ago as a way of insulating copper wires from shorting out to ground. So, conductor lets the electricity flow, insulator blocks the flow. Excuse me. So what's interesting is that pure water is actually an insulator. If you have distilled water, it will not conduct electricity, but water is a powerful solvent, and it likes to dissolve stuff. And as soon as water starts to get impurities in it and dissolve things into it, especially salts and metal compounds, then it begins to start acting like a conductor, which is why we think of it as being somewhat dangerous to have electrical appliances, around a bathtub or other, bodies of water. And so normally we'll just think of water, the kind of water you'll be dealing with in real life, as a conductor, and therefore we have to be careful around it. The other interesting thing is that air acts as a very good insulator of electric current, to keep electric current from flowing. So this is one of the places where you have to kind of think about it. We're going to talk more about this analogy of electric current being like water flowing through a pipe, but if you just have a pipe and you leave it open and there's got some water pressure behind it, that water will just come out and spill out on the ground, because the air actually doesn't really provide any resistance to the flow of that water, very little. But on the other hand, air acts as a really good insulator, therefore it provides a lot of resistance to the flow of electricity. For those of you who are a little more technical, it's basically 3 megavolts per meter is the insulating capability of air. And what that means is that in an electrical circuit, if we have a wire that's just hanging out there in the air, it can have a lot of voltage on it and be dangerous, and it won't actually let any current flow until something touches it that provides a path for electricity to flow that is something of a conductor. So just something important to think about, that air is an efficient insulator. And that brings us to this idea that electricity needs a complete path or a circuit in order to flow. And if you have what we call an open circuit, then it won't. So don't worry about all the little symbols in this diagram. This is a little circuit diagram. Just look over at the far left-hand side. There's a little thing called S. That's a switch. And at the moment, that switch is open. And what that means is the battery, which is the little thing down at the bottom labeled E, doesn't have a complete circuit. And so no electricity will actually flow through all the rest of the little devices that are there on that schematic. Don't worry about what they are too much yet. But what that means is until that switch is closed and we have a complete path from the positive side of the battery to the negative side of the battery, then no current's going to go anywhere. So yes, the thing on the very bottom that's a long line and then a short line and a long line and a short line, that is a symbol for a battery. And so you have to actually have a circuit between the positive and the negative sides of the battery so that the battery can push the current through the circuit. So if we were to close that switch, then power could flow, electricity could flow, and if we were to open it back up, it would stop. Very important thing to understand, that we have to have a complete path in order for our electricity to flow. So one of the other important things to understand is electricity will tend to follow the path of least resistance, kind of like water wanting to flow downhill. But it will flow in parallel through all paths that allow for a complete circuit. So the little diagram I have here, again, is a battery. And those are 3 resistors. Don't worry about that too much yet, but there are 3 things that electricity could flow through. And if you notice, they're all connected in parallel to each other. In other words, all of them provide a different path for electricity to go through. And what will happen is that just like if we were to put water pipes here and put a T at each one of those little junction points, water would want to flow both ways as long as there was some pressure pushing it and there was a complete path for it to flow. So you can kind of think of that battery almost like a water pump trying to push water, and the wires that you see in the diagram almost like pipes. And you can imagine that electricity or the water would flow through all three of those parallel resistors, provided that there wasn't some other blockage in the pipes. So the reason that's important is, well, not only to understand how the circuit works, but also for safety. Because if you happen to touch the wrong thing at the wrong time, in the wrong, you can wind up being a path of electricity, and you can end up being electrocuted. So that's just important to bear in mind from a safety perspective. We'll talk about that a lot more later. So with that little bit of background, we're ready to talk about 4 technical terms that we'll be using over and over again throughout the series. That's when we're talking about current, voltage, resistance, and power. So let's kind of jump into it and think about it. Current is the amount of electricity that is flowing through a circuit. You can think about that as sort of like the amount of water flowing through a pipe. So if I have water flowing through a pipe, I'm probably going to measure it in something like gallons per minute or liters per minute. When I measure the flow of electricity through a circuit, we use a unit called the ampere, often shortened as amp, and abbreviated with the letter capital A. And really all an amp is a certain amount of electricity flowing through a wire. So just like I could look at a pipe and say, oh, there's, say, 5 gallons per minute flowing past that point on the pipe. Well, if I looked at a wire and said there's 5 amps flowing through that wire right there, all I'm really saying is that's a measure of how many electrons are being pushed past that point on that wire at that given time. So it's the amount of current going through that wire. The next concept is really voltage. And I've noticed a lot of people, when I ask them questions, they get confused by voltage. But voltage is the electromagnetic pressure that's pushing the current along through the circuit. And we call that pressure the voltage. So if I were going to be measuring water pressure in a pipe, I could use like pounds per square inch. And that would tell me how much pressure there was trying to push that water. In electrical circuit, that pressure, we call it voltage, and we use the unit of a volt. And really, when we measure voltage, what we're going to be doing is we're going to be measuring the difference in potential between 2 different points. What that means is we're going to look at the pressure at one point and the pressure at another point, and we're going to say the voltage difference between these 2 points is a certain amount. And that pressure difference is going to tell us how much current is going to be pushed through that circuit. So now we have current measured in amps, the amount that's flowing. We have the pressure measured in volts to tell us how much force is trying to push that current along. The next part would be the resistance to flow that is being provided by the wire or the electrical device that the current is flowing through. Using the water analogy, if we use a smaller pipe, we know that that's going to actually resist the flow of water bigger than a big pipe. It's going to have more resistance. So if I use a smaller pipe with the same amount of pressure pushing on it, like I have a pump that puts out, let's say, 20 pounds per square inch, and I put a little small pipe on it, well, it's going to push less water than if I use a bigger pipe with less resistance. And in electrical circuits, same idea. A wire has resistance, and electrical devices have resistance. And it's also true that little thin wire tends to have more resistance, and big wire tends to have less resistance. We measure the resistance of an electrical device or a wire to the flow of electrical current in a unit called ohms. And the symbol is the omega symbol from the Greek alphabet. So now we have current, the amount of flow in amps, voltage, the amount of pressure measured in volts, and resistance measured in ohms. And the last concept I want to introduce at this moment is power. If we are looking at water coming out the end of a pipe, then we could ask, well, how much power is behind that water? And you look at it and you go, well, it would be the combination of how much water is coming out and how much force it's coming out with. And that would actually determine the amount of power behind that water. Power in physics is defined as the ability to do work, and it is a measure of the rate of flow of energy. In an electrical circuit, we measure power in the unit of a watt. And for, again, people who are a little more technical, a watt is defined as 1 joule per second. So it's a rate of flow of energy. The more wattage we have, the more power we have, the more work we can make that electrical current do for us. And when we want to actually get a number for how many watts we have, we do that by simply multiplying the voltage times the current. So if I have a 12-volt battery and it is pushing 2 amps, then 12 times 2 is 24 watts, and it's just that simple. I've used another example down below on the slide. If you have a current of 2 amps going through 10 volts, then we're using 20 watts of power. So that's just as simple as it is to get the power. Now, when we get into AC circuits in a little while, we'll talk about some cases when it's a little more complicated, but for right now, that's all you really need to know. So we've got current in amps, pressure in volts, resistance in ohms, and power in watts. Keep on repeating those because I want you to start to kind of get an intuitive understanding of what those things are and not to be confused when I use those as we go forward. So we did a real quick little video that just reviews these concepts, and I'm going to play it for you real quickly. I slowed it down from last week in terms of bit rate, so hopefully everybody will be able to see it streaming to you without too much interruption. So it's about 4 minutes. It's just a great little review, and I'll be back on the other side of the video.
So one of the challenges for a lot of people when trying to think their way through electricity is it's kind of hard to see. A lot of time, most of the time in electrical circuits, you can't see what's going on. And so I found it really useful to kind of use an analogy of water flowing through a pipe. So what I'd like to do is do a quick review of a couple of the basic concepts of electricity, using a hose and some water just to help us think our way through what's really going on. So I've just got a hose with water flowing, and even though the analogies with electricity is not perfect, it's actually pretty good. The first thing to think about in electric current is the flow, which we measure in amps, just like we would measure the water flow coming out of the hose here in maybe gallons per minute or so. And the next thing we would think about in electricity would be the pressure pushing the water out of the hose, which would be voltage. Here in a pipe like this or a hose, that would be maybe pounds per square inch. And then the last piece would be the resistance of the hose or the pipe itself. In this case, just got a regular, garden hose, and it's providing a certain amount of resistance to the flow of water coming out. And obviously, if I kept the pressure the same and used a bigger pipe with less resistance, I get more water flow. On the other hand, if we use a really small hose with the same amount of pressure, we get less water flow. So this is really a core way of thinking about electricity flowing in a circuit. We have the amperage, the current, which is the amount of current flow measured in amps. We have the voltage, which is the pressure pushing the current. And then we have the resistance, which is the amount of pushback that whatever it's flowing through is giving you. And that together determines a lot about what kind and amount of current is flowing. So I've just taken and turned down the pressure on the hose just a little bit, and obviously the amount of current coming out, the amount of flow coming out has gone down. Just like in an electric circuit, where if we reduce the voltage, keep the resistance the same, we're going to get less current. So this is why it's kind of helpful to think about voltage, current, resistance as water flowing through a pipe. Very similar relationships between amount of flow, amount of pressure, and resistance. The last thing I want to talk about is power. And that's the ability of the stream of electricity or the stream of water to actually do work. And the way we get power in electric circuits is we multiply the current times the voltage. And that gives us the wattage, the total amount of power. So in a stream of water, you want to think about how much work you might be able to get out of that water. It would be the product of how much flow you had times the amount of pressure behind that flow. That's exactly the same in electric current, where if I take and increase this pressure but keep this flow the same, that water's coming out with a lot more force behind it, and as a result, it's going to have a lot more power behind it. We do that a lot of times if we want to send the water out farther, get more power behind it, we might just take our finger and do this. We're restricting the water flow, but we're putting more pressure behind it, and the water goes a lot farther. So, same thing in electrical circuit. You put more voltage behind a certain amount of current, you're going to get more power. And so that's just a really quick way of thinking your way through how resistance, voltage, current, and power actually relate to each other in an electrical circuit.
All right, so hopefully I'm back, and I'm just going to check in and make certain, Wayne, you can, or Mark, you can see me and you can hear me and you can see my slides again. Make certain we're good to go.
You're good for my end, Alan, and
Okay.
Everybody throw in some run. Make sure you got it.
Very good. All right, so this is a good point. We're about halfway through, and now I'm going to kind of speed up. I know I repeated myself several times there, but I've noticed that with these very fundamental concepts, that if I don't do that, if I just go through it really quickly, sometimes it can end up being kind of confusing. So if anybody still has questions or is confused, please go ahead and throw some questions in for us, and I'll try to clarify. But while we're waiting for that, we'll just go ahead and keep on moving forward, and hopefully we'll get any other questions. So Wayne or Mark, just interrupt me if we have questions we need to be dealing with. So the next thing I want to talk about is the two main types of electricity that we're going to be working with in solar PV, or actually in all the different applications that we're going to be doing. and that's direct current and alternating current. DC, direct current, AC, alternating current. And the difference is that direct current is basically, well, it's intuitively what you would think of from the analogy we were using for water in a pipe. It's like you have a pump, and it's pumping water, and the water is just going in one direction. You have a steady stream of water going in one direction. And that is basically what direct current is like. You have a voltage that is typically staying the same. It's just like having the same amount of pressure in a pump pushing on the water through a pipe. And the result is that the current is typically the same if it's going through just a pure resistive circuit. It's just going to be so in the slide, hopefully it's showing up now, you'll see that the red on the little diagram is direct current, which basically means that you've got like an amp and it's flowing in one direction, just stays steady. The other kind of power we're going to work with is alternating current, AC. And this is the kind of power that comes out of your wall outlet. We'll talk about that more in a moment. But what it does is it actually alternates directions. And if you want to think about that in terms of our water in a pipe analogy, then it would be like we have a pipe with water flowing in it, but what happens is the water is flowing in this direction, and then it slows down and stops, and then it flows back in the other direction, and it slows down and stops, and it goes back and forth. And so what happened would be, there'd be a moment when it would stop, so it would be at zero, then it would start moving back, get faster going the other direction, and then it would slow down to a stop, and then it would turn direction and speed up and slow down to a stop and go back and forth and back and forth. And that's what alternating current is. The voltage, that is the pressure pushing on the current, goes back and forth. It's almost like we had a pump that did something strange. It'd be strange for a water pump to do this. If we had a water pump that would like push the water one direction for a little bit and stop and push it back the other direction in a pipe that was going around like this. And we would end up with the current in the pipe actually going one direction and going back and forth and back and forth. And that would be alternating current. So that's the distinction between the two types of power we're going to be working with: direct current, DC, alternating current, AC. So DC, of course, that's the kind of power that our batteries produce. And you know, your battery has a positive terminal, a negative terminal, and just produces a steady voltage. And when we hook up a circuit to that, then it's basically just going to try to push the current in one direction all the time. And by the way, that's a little crown battery there. That's the kind of deep cycle battery you might use in a solar electric system. Okay. Just to give you some numbers, start wrapping your head around, the most common voltages for battery systems that we're going to be working with are 12 volt, 24 volt, and 48 volt DC. And that VDC at the end stands for volts DC. And what you're going to find out is we're going to have a whole session on batteries and storage and everything, that in a lot of cases we're going to end up with a bunch of batteries and be chained together in different ways to provide the voltage and the storage capacity that we actually need. But they're going to be providing DC or direct current kinds of power for us. And then alternating current. Alternating between positive and negative, causing the cycle to go back and forth. So it changes direction each half cycle. And that's the kind of power that your utility company is going to provide pretty much all over the world. You're always getting AC power pretty much all over the world. And it's going to be, we're going to talk about that a little bit later, it may come out with a different frequency and a different voltage, but it's going to be AC coming out of your wall plug. just another little note is if you have a portable generator, like a little diesel generator or propane generator, a gasoline power generator, the vast majority of those are set up to also produce AC power output, so that you can basically plug in anything you would plug in your house. You can plug it to that generator. An important thing about AC voltage is that when we talk about voltage in AC, we don't actually talk about what we would call the peak voltage. That is, if you see on this little diagram, V sub P is the voltage peak. That's the highest value that the voltage gets to. When we talk about voltage of an AC circuit, we don't actually specify that peak voltage. And we also don't specify the peak-to-peak voltage, which is over on the right-hand side of the diagram where you see V sub PP. That's the peak-to-peak voltage, which will be twice the peak voltage. Because what's going to happen is in the first half of the cycle, the voltage is going to go up to a certain value, positive, and then come back down to 0. And then the second half of the cycle, it's going to go negative and go down to the same value, negative, that the peak was positive, and then go back to 0. And that creates an entire cycle. So it turns out, for a number of reasons I'm not going to get into right now, that the peak voltage, because we only hit that peak for just a moment, that peak voltage is not a very good number to use when you're trying to figure out how much power is coming out of a circuit that's being pushed by an alternating current voltage. So we end up using this thing that's called an RMS voltage, which stands for root mean square. And the root mean square voltage is gotten by taking the peak voltage and multiplying it by 0.707. And that will give you the RMS voltage. So if you're here in the United States, for example, and you're told that the voltage coming out of your wall socket is 120 volts AC, that's not the peak voltage. That's actually the RMS voltage. And that's what you're being given. So just understand that no matter where you are in the world, whatever value you're being told is your wall outlet voltage, that's the RMS voltage. And whether you're, in a lot of areas in the world, it's between 220 and 240 volts is very common. So that is RMS, or root mean square voltage. So, the standard voltage coming out of a wall outlet here where I am in the U.S. is 120 volts AC. That's, of course, the RMS voltage. We also have some outlets here that are providing 240 volts AC, and they're used for devices like stoves, clothes dryers that require more power, a lot of power. And the little picture I have here in the lower right of this slide is actually a receptacle that we use here in the United States for 240 volt to feed a stove or electric range. And what's interesting is that 220, 240 volt is actually pretty common in other locations around the world as being the voltage that's provided as a normal wall outlet. Whereas here in the United States, our normal wall outlet that you just plug your normal loads into every day is 120 volts AC. So the next thing we need to talk about AC power is basically how fast is it going back and forth? How fast is it cycling? And how long does each cycle take? And when we start talking about that, we specify that in a unit called Hertz, which is simply the number of cycles per second. So if I had a voltage that went up and then came back down to 0 in half a second, and then went back down and back up to 0 in the second half of the second, so that it took 1 full second to cycle, that would be 1 hertz. It would be 1 cycle per second. If we were to double that, so that it went up and up on the first quarter second, and then down on the second quarter second, and then up on the third quarter second, and down on the third quarter second. I had 2 complete cycles in a second. It would be 2 hertz. Keep on just getting faster and faster, and we get higher frequencies. The standard frequency for AC power in the United States is 60 hertz. That's used some other places around the world, but a lot of places around the world actually use 50 hertz. So the diagram that you're looking at shows what, in red, shows what wall outlet current looks like in the United States. You can see that RMS voltage is around 110 and 120 volts. Peak voltage is a little over 150, and that it is going through an entire cycle in something like 16 to 17 milliseconds. That is 16 to 17 thousandths of a second. Whereas the blue line is showing us what it looks like in, say, an area of the world where they have 230 volt RMS voltage with 50 hertz. And so you can see it's actually cycling a little bit slower than the 60 hertz. It's only cycling 50 times in a second instead of 60. But the peak voltage is much higher, up around 325 volts. So if you could take something like an oscilloscope, which is a device that would let you look at this and watch what was coming out of your wall outlet, this is about what you'd see for coming out of a wall outlet in a standard home or building anywhere in the world, something like this. So the piece of test equipment we use to measure voltage, current, resistance is called a multimeter. And this is a critical piece of test equipment to have when you're working on electrical circuits. To me, I just think it's impossible to work safely on any electrical system without having a good, proper multimeter. What it is, and I'm going to grab my multimeter. I have it here on the table behind me. This is my multimeter. I happen to like Fluke as a brand, but there's a lot of great brands out there. And it will allow you to measure. There's different places on the dial here. If I turn it to here, it's going to measure AC voltage. If I turn it here, it's going to measure DC voltage. I can turn it here and measure millivolts for measuring very small amounts of voltage. And then I can turn it here and it'll measure resistance of a circuit. I can see how many ohms. And then it also has what's called a continuity tester, where if I put the leads of the test equipment onto something that is a short circuit, it'll beep at me to tell me that I've got a connection between between whatever the 2 leads are touching. So I'm going to put the leads on here so you can kind of see what this looks like. There you go, I've got the leads on it. And I've got it on continuity right now, so you can hear that maybe. That tone tells me that when I touch these 2 together, that I've got a complete electrical circuit with very low resistance. So this is something that every electrician will be using, and when you are working on any circuit, one of the very important safety things to do is to use this to make certain that the circuit is properly de-energized, doesn't have voltage on it, before you start working on it. And so that's part of the reason it's such a critical piece of safety gear, is to have a good multimeter to get you to work with. The last 2 positions I didn't show you were both for measuring current. So it's called a multimeter because it measures a number of things. It measures voltage, it measures resistance, it measures current. So very important piece of test gear to have when you are working with electrical circuits. So one of the important things to realize is that a lot of our electrical devices use DC voltage internally even if we typically sometimes plug them into a wall. So for example, the computer monitor that I'm looking at right now as I'm doing this presentation, it plugs right into the wall outlet with an AC